Welcome to us. In this video, we're going to look on vapor power cycles. Okay, so I'll give you a question. In a Rankine cycle, the steam within the turbine is saturated. So the reason why I've highlighted though it's saturated because it tells us a lot of things. We're going to look at it. Okay, so it's saturated at a pressure of 35 bar and the exhaust pressure is 0.2 bar. Determine the pump work, question number 1. The turbine work, question number 2. The Rankine efficiency, question number 3. The condenser heat flow, that's going to be the fourth question. And the dryness at the end of the expansion, that is question number 5. And also given additional information. Okay, so assume the flow rate of 9.5 kgs per second. Okay, so on this question, the questions may not come in order like this one. So from here, I think we're going to finish with the Rankine efficiency. That's the last thing that we're going to look at. So if an examination, just have to write everything working, then just draft it as it is. Okay, but there's no way you're going to calculate the Rankine efficiency without knowing the condenser flow, that calculating turbine work. So that's what we're going to do. Okay, so what are we going to do first? So first of all, we have to sketch a graph, a Rankine efficiency graph. Okay, so that's what we want to do. Okay, so let's do that. So this is the graph that we have. So the graph is 4 states. So state number 1, that is where we're going to have the turbines, right? That we're going to have the turbines rotating. State 2, we're going to have a condenser, right? So the turbines being rotated by the steam. So when it comes to condenser, we're going to have fluid. And state number 3, we're going to have a pump right there. Okay? And on state number 4 and 5, that is going to be the boiler. They're going to boil so that we can have the steam at the turbine. So in the cycle is going to repeat. So that's what you have. And the graph is a temperature against entropy, right? This is temperature against entropy. That is very important because in some cases we're going to use entropy to find missing values. So on state 1, if we say H1, that means we're going to look on state 1, H2, state 2, H3, so on, right? Okay, so what is the given data that we're given? Let's look. We're given the pressure, right? The inlet pressure, the turbine, 35 bar, and it's wise, since most of the steam table don't have bars, they do in kilopascal or pascal, so I'm going to change it, right? So it's 35 times 10 to the power 2 kilopascal, because a bar is equal to 10 to the power 5 pascal, right? And now I'm going to go to the exhaust. Yeah, what is the exhaust pressure? 0.2 bar. Changing that to pascal, it's going to be 0.2 times 10 to the power 2 kilopascal, or just 20 kilopascal. Okay, and not forgetting our mass flow rate. Okay, so now let's go and solve on those questions. So starting with the pump work, right? That's what we're going to start. What is the formula for pump work? So pump work, we have two formulas. The first one includes the pressure, and the other one is by using the enthalpy at different states. Okay, so now there are some things that you have to know. What is F on a steam table? So F just means saturated fluid, and G means saturated gas, and FG, that means vaporization. So you have to be familiar with that, because in states you are not going to be told in exam which value of enthalpy are going to take, the one with saturated fluid, gas, or vaporization. So you have to know that in state number 1 there's going to be gas turbine, so I'm only going to deal with gas. In state number 2 it's condensation, that means I'm going to deal with the fluid. So that's what we're going to have, right? Okay, and write the data that we have. P1 3500 kilopascal. Okay, so this is the steam table, so it doesn't matter, yours may look different, but this is a standard steam table, and some of the values, as you can see, weight is still 1.7, 1.68. In some cases you may see it's 1.71, 64, 6 watts. So it's just a matter of different numbers, but the procedure is just the same, right? Okay, so on state number 1, what we're going to have, we're going to have what we call Hg, that is enthalpy for gas, and that's what I'm going to call H1. I'm going to do with gas, both our own turbines. So that's what we're going to have. Okay, so if you go on steam table, and we're going to go to 3500, right? I've highlighted 3500 as you can see. And now we're going to go is Hg, that means enthalpy for the gas. Okay, and as you can see, it's 280217, and I'm going to write it there. What we're going to need is, that's how we can take values on a steam table, right? State number 1, we're dealing with gas. Okay, now let's go to entropy. We're going to need entropy. It's also Sg, because we're going to do with gas. So to 3500, we're going to go along to 6.1200, as you can see, and we're going to write that value. Okay, that's what we're going to need for state number 1. And x1 is equal to 1. And what is x? X is the dryness fraction. But as you can see from our question, that's why I've highlighted the word saturated. So if something is saturated, that means the dryness fraction is equal to 1. Okay, and now I'm going to go to P, pressure 2, the exhaustive pressure. So you can see it's 20 kilopascal. So I'm going to flip on other page of my steam table. going to second pressure, right? Okay, so now I'm going to go to 20 kilopascal. So go to 20 kilopascal, I've highlighted it as you can see. And now we're going to find HFY. State number 2 is condensation. There's going to be fluid. So we're going to look on saturated fluid. Okay, so what is HF? HF is 251.31. We're going to write it down. Now we're going to go to HFG. We're going to need it 2358.65. And we're going to go to VF. We're going to need the volume. Okay, we're going to use it, right? Okay, and what is the volume? Going to write it down right here. Going to get it on column number 3. Okay, and now we're going to go to SF, going to the entropy for the fluid, right? And we're going to also need SFG. I'm going to write it, which is 7.0777. Okay, so this is the information that we're going to need. So in examination, write this information down. They have some marks on them, right? So I have two formulas. The first one includes pressure in the volume, and the other one is about enthalpy. So the first one is VF2 P4 minus P3. So the subscript 2 means that one state number 2, and 4 means in state number 4. It's the one which includes enthalpy. So it's enthalpy in state 4 and enthalpy in state 3. So as again, look, we're going to have our pump. Our pump is located at state number 3, right? So to find the pump work, we're going to say enthalpy at state number 4 minus enthalpy at state number 3. But there's another way which we are going to use right here, which includes volume and pressure. Okay, so now we have the volume it's 0.0177 right here, and the pressure, so the pressure P4, since the pressure is going to be the same right here, pressure at 4 is going to be equal to pressure at 1. So it's just the graph, that's how the graph is drawn. But in some cases you may see that 4 will be up here, okay, and pressure at 2 and 3 will be equal, pressure at 1 and 4 will be equal, right? So 3 and 4, those are exhaust pressure. 4 and 1, those are inlet pressure, right? 3 and 4 exhaust pressure. So if we calculate here, we're going to get 3.5496 kilojoules. Okay, so that's what we have. Okay, so now we're going to go to turbine work. So turbine work, what is turbine work? So this one is going to include state number 1 and state number 2. So it's going to be H1 minus H2. So let's write the formula, but we're going to include the mass because we're going to need the volumetric mass flow. Okay, so that's M, but you can write M and a dot on top of M. That is the format for volumetric mass flow. Okay, so now from here, as you can see, our state number 1, we have it, and we have H for state number 1, which said it's HG. But what is H2? We don't have H2, but we have the formula for calculating H2. So the formula is HF2 plus X2 SFG2. So S entropy, X and X Lorentz fraction in the second state, and HF2, that means we're going to find the enthalpy of the saturated fluid at state number 2. But there's the other thing, I don't know if I noticed it, we don't have the Lorentz fraction as state number 2. And if we find this Lorentz fraction, that's answering the question which required us to find the Lorentz fraction at the end of the expansion. Okay, so that means we're going to find two unknowns. So what are we going to use? So if we look at our graph, we have state number 1 and state number 2. As you can see, the value of entropy right here and the value of entropy is just the same as state number 1 and state number 2. It's just simple geometry from the graph. The coordinate of entropy right here and coordinate of entropy just the same. So we're going to use entropy to find state number 2, right? To find X. So if we just write simple equation, S1 should be equal to S2. Because I said those entropy are the same. Let's do that. Okay. So S1 should be equal to S2. That is going to be equation number 1. But also, what is the formula for finding the entropy? We have an independent formula which does not include equating these two entropies together. Okay, that's one is S2 is equal to SF2 plus XFG2. So if it is 1, just put 1 on subscript 2. So now let's do that. I'm going to call this equation number 2. We have 2 equations. I think we can solve it. Okay, so from question number 1, that's the question I'm going to write, which is going to equate everything. So we have for S1, when we have it from the values that we have calculated, that is SG1 6.122, and for SF2, go to state number 2 on our given data. Going to look below P2. As you can see, SF2 is 0.813, and X2 don't have it, but we have SFG2 7.077. Okay, that is good. Now just going to solve this simple equation. So first of all, we're going to subtract 0.813 from both sides, and we're going to left with this one. And I think I can just divide by 7.0777 to be left with x. And if we do that, we're going to have this, and we're going to have our x2 0.7475168848. Okay, so in some cases we may write this as a percentage, but just good to write it as decimal since we're going to use it as a decimal. So with this, you can find our enthalpy state number 2, right? Okay, so enthalpy state number 2 is HF. H2 is equals to HF2 plus X2 HFG2. Okay, so now it's a matter of plugging in results. We're going to go to our values, state number 2 under P2, right? Okay, so if we do this, let's see what is going to happen. Okay, so let's just make some space right here. And now H2, for HF2, we have it, which is 251.31 plus 0.74, that is X2, and we're going to multiply that by HFG2, that is 258, which is right here. Okay, and if you do that, we're going to get 2014.44. That is going to be the value for H2, right? Okay, and now our turbine work is now simple. What we're going to do, turbine work for the mass, we have the mass H2, H1, which is 2.17 minus 2014.44, and now let's put the mass, which is 9.5, and if we subtract, you're going to get 787.73. And as you can see, we have our answer, and you can write it in kilojoules or in watts, right? So as you can see, we have 7,494.5. So if you compare the work of the pump and the work of the turbine, the work of the pump is very, very, very small. That in some cases, when some people want to calculate the Rankine efficiency, they just don't include the work of the pump. Why? Because it is very small. But you have to do that when you are told to not include the work of the pump. Okay, so now let's go to the next question that's going to be dryness at the end of the expansion. That dryness fraction is set number 2, right? We've calculated it. Okay, so just going to write the answer right here. So this is the answer. Now we're going to go to the condenser heat flow. So the condenser is going to work, so there's going to be heat. So what we're going to do, just going to use our state to calculate it from this graph, the temperature entropy graph. Okay, so it's going to be mass H2 minus H3. So this is the region for the condenser, which is right here. By subtracting the enthalpy, you can calculate the work. Okay, and we have everything we need from our formulas, as you can see, right? That's what we're going to use from those two. Okay, so now we said H3 is HF2. Okay, since we're going to, this is fluid, so the enthalpy right here and the enthalpy right here is going to be the same. Okay, and that is going to give us 251.31, putting it at our values table. Okay, so mass 9.5, H2 have it 2014.44 minus 251.31. So you have to make sure and calculate those enthalpy, because one wrong answer will affect the whole thing. As you can see, we've reached H2 in 3 cases right now. So that means if it was wrong, everything's going to be affected. So you have to you have to be very careful. Okay, and now this is the answer. I'm going to put it in kilowatts. Okay, and now finally we're going to calculate the Rankine efficiency. So this one is just the network over the total work done, right? So this is what we have. Okay, so I'm going to write it, the formula, it's H1 minus H2. So in this case, we're going to include the work of the turbine, but if you want, you may just subtract the work done by the pump on top, right, to find the net work done. Since the work done by the pump is small, that's why I've excluded it, right? And below I'm going to write H1 minus H3, and normally we express this as a percentage. Okay, so our value is H1, we have it, we're going to write all the values H1, H2, and H3, right? And now we're going to plug it in, right, and multiply by 100. And if we do that, we're going to get our answer is 8.88%. So thank you for watching. If you like other videos, check in the description, and may show love by liking and subscribing. Thank you for watching.